Okay, so today, well, on this video, we're going to be looking at with some examples of how to use the congruence rules. Okay, so we've gone over them, the different rules for using congruent triangles. So what we're going to do now is we're going to look at some examples of using them, because we didn't go through a lot of them, and to be quite fair, these might have been some of the first times that you've seen these things, and that's fine. Why should we bother doing this? Well, these congruence rules really give you an introduction to three areas of mathematics that I want to talk about. We've got introduction to proof. Okay, now mathematics is one of the few areas of science and of any part of life where you can absolutely prove something. Okay, so it might sound ridiculous, but you can draw up proofs for things like, why is it that 2 plus 2 is equal to 4? Okay, we can do a proof around that. We can muck around with different things that prove that this particular equation works for all possible times, right? For instance, when we looked at Pythagoras' theorem, the reason why it's a theorem and it's not just a theory is it's been proved that with the right angle triangle, a squared plus b squared, so the square of the sides added together is equal to the square of the hypotenuse. That is proved. It will always work for any right angle triangle on a flat surface. Okay. Additionally, these congruence rules will help you with logic, which is a mathematical area where you're looking at answering questions with a mathematical argument. Okay, and starting to think this way using quite easy examples like congruent triangles will really help you with that. Okay, and pure mathematics is one of my favorite areas of mathematics, which is looking at the absolute basic, well, not basics, the core of mathematics, not worrying about the fluff of arithmetic or calculations, really just going into how do these numbers behave. Okay, so that's sort of what we're looking at, some introductions to that stuff with these congruence rules and using them. Right, so my first example here, I've got two triangles, and even though you might be able to look at them and say, yeah, I mean, they're absolutely congruent. They look pretty much the same. It's just been turned. Yep, fine. But how do we prove that that's the case? Well, we've shown before that there are these different rules. Remember, we have let's just write them up the top here. We're going to use a couple of different rules. So that is SSS, so side, 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 SAS, AAS, or RHS. So remember, that means that if you have a side, side, side of a triangle, a side, an angle, then a side, an angle, angle, side, or a right angle triangle where you have the hypotenuse and one of the other sides, that you can work out these other angles. Okay. You can work out whether two triangles are congruent, because these are our rules. Okay, if we can find one of these rules that fits these two triangles, then they are congruent and it will work. So let's have a look at what we've got here. We've got a triangle here. We have an angle of 70 degrees, an angle of 60, and a side. So we have two angles and a side. We might be thinking about, well, this one here, angle, angle, side. So let's investigate. So our 70 is here, they correspond to each other. This 60 corresponds to here, and this 5 centimeters corresponds to here, and they're all in the same position. If we rotate this triangle here, we will get this one with the 70 in the same position, the 60 in the same position, and the 5 in the same position. So we have two equal angles and an equal side, and so that means that we can use the AAS rule, okay? Because we've got 70, 60, 5 centimeters, okay? So that means we're going 70 degrees, 60 degrees. This is sort of the order as we look around our triangle. 70, 60, 5 centimeters, 70, 60, 5 centimeters. Okay, so we have the AAS rule here. Angle, angle, side. So these are congruent. Yes. Okay. Right. Let's move on to the next one. Okay, immediately when you see these triangles, you should be thinking straight away, what kind of triangle have I got? I have a right angle triangle. So I'm really going to be looking for a way to get the RHS rule to fit. Okay, which means, remember, when you have a 90-degree triangle, right angle triangle, and you have a hypotenuse and one of the other lengths, and that they correspond to each other, then we can use this RHS rule to say that yes, they're congruent. So let's have a look. Okay, they're both right angle triangles, so tick, that works. Okay, let's have a look. They both have a hypotenuse of the same length. Cool, that works too. So 2 out of our 3 criteria are working. We have a right angle triangle and we have a hypotenuse that are corresponding as well. Okay, so 15 meters, 15 meters. Right, let's have a look at our other one, 12 meters and 12 meters. So are they in the same spot, you need to ask. So they both are sort of sharing this, the smaller angle out of the 2. So we can actually say that yes, these are in exactly the same position. So yes, these are congruent because of the RHS rule. Okay, tick, and we just say yes, this is or these are congruent. Okay, so in the exam and in other areas of life and mathematics, you won't just be saying, oh, these are congruent, RHS rule. You'll want to use your understanding of these things to be able to come up with ideas about other triangles based on what you know about congruence, okay? And this is especially to do with the quadrilateral stuff, okay? So please make sure you have a look at a lot of examples. There's only one I want to go through because that's sort of a platform that will help you have a look at the rest of your congruent triangle issues, okay? So what do we have here? Good old parallelogram. We have the vertices A, B, C, and D, and we have E as this midpoint here. Remember that our diagonals bisect each other, so these are the same lengths as far as our quadrilaterals are concerned. But what we're being asked here to do is to prove that diagonals bisect each other. I've told you that in the previous video. I just told you it right then. But why is the question we're asking. Why is it so? Can you prove it to me? The answer is yes. But let's have a look at it and think. How can I tell that this length and this length are the same, and this length here are exactly the same? How can I tell? Well, you need to think about, what do I know? What do I know about angles? Okay, especially angles on a transversal. Okay, so remember when we've looked at before at angles on a transversal, so across parallel lines especially, because since we've got what? Parallel, those kind of things go bing, ding, ding in your mind straight up. So remember, we've got a couple of different things. So we've got parallel lines here, terribly drawn as usual. Right, we know that these angles here are the same. They're corresponding to each other. We know that we have these angles here are corresponding to each other. Okay, they're alternate angles. And we also know that these angles here add up to 180. And we also know that this angle and this angle are vertically opposite, so they're exactly the same. Those are the 3 kind of rules and ideas you've got to remember when you're attacking these problems. How do I suppose, remember when we've been doing compound areas, okay, and compound perimeters. You think about, where in this area do I find my smaller pieces to be able to work out the bigger piece? So for this one, you think to yourself, where can I see bits and pieces that I already know about that I can apply to this one here? Okay, so what I'm going to do is I want you to have a look at our parallelogram here and see if we can find something that's shaped like this. Okay, so what I've done in our next video, in our next little slide down here, is that I've taken our parallelogram and I've deleted the lines AD, CB, and DB. So I've deleted the line that used to be here and here, and I've deleted the diagonal that goes this way as well. Okay, good reasons for that. So what do I have here? Let's just extend this line here and pretend that I have a transversal over parallel lines. So what that means is that I can categorically say, without even having to worry about it, that this angle here and this angle here are equal because they are alternate angles across a transversal. Okay, so they're on alternate sides of the transversal and in the same kind of spots, so that means that they are, without a doubt, equal to each other. Okay, so that means that we can say that the angle BAE is the same as angle DCE. Okay, so I've just said angle BAE, which is this one here, BAE is the same as angle DCE. Okay, so I've just told you that those two are the same angles. Why? Because of the transversals across parallel lines rule that we've looked at previously before. Okay, we can just use that, and that's all you need to write. In fact, I think we've used before the little code thing. It goes like, is actually in this shape, and we just show that it's equal across transversals. Okay, parallel transversal. Might draw that even a little bit better for you so you can see what's going on. I think the Z kind of rule is what we've looked at it before, so because of that. Okay, that's all you need to do. That is equal to that. Right, there's the first step of our proof. Right, second one is to investigate the other transversal. So still the same lines, so I've deleted the ones that were here and here, but I'm looking at this diagonal this time. Okay, again, we've got, just imagine with me please, we've got a transversal that goes across these two parallel lines, DC and AB, and we know that when we have a transversal across parallel lines, that our alternate angles across the transversal are going to be equal. These two here. So we can say categorically, without a doubt, that the angle ABE is equal to angle CDE. Okay, so this angle here is equal to this angle here, and that is because of the alternate across a transversal and parallel lines rule. Okay, so something that we've learned a little bit earlier. So that means that we can go a little bit further thinking about our properties of quadrilaterals. Let's have a look at it. Let's move down for the quadrilaterals. So what we know so far is that angle BAE is equal to angle DCE, and angle ABE is equal to angle CDE. Okay, so we've essentially said that this angle is equal to this one, and this angle here is equal to this one here. Okay, right. What do we know about parallelograms? We know that lines AB is equal to CD. Okay, this line here is the same length as this line here. We know that because it is a parallelogram. We don't have to worry about testing it or anything. We know that it is because it is a parallelogram. Right. Essentially, therefore, we know that this length here and this length here are the same. So now we borrow what we've been learning about congruent triangles and we investigate this triangle here, triangle 1, and this triangle here, triangle 2. Okay? Right, what do we know about it? We have two corresponding angles that are the same. Okay, two angles that are the same. And in between those angles, we have a side that we know is exactly the same. So let's think about it for a moment, and we can say categorically, because of our congruence rules, that triangle ABE is equivalent to triangle CDE. Okay, because of AAS, okay, or ASA really, because it's angle side angle. Just fix that up. Doesn't remember when we looked at that rule, it doesn't matter what order it is in. So angle side angle. Okay, we have angle side angle, angle side angle. Therefore, we can finally say that because these are congruent triangles, so I'll just scroll down a little bit more. So finally, therefore, because the triangles are congruent, okay, which means that everything about them is exactly the same, like lengths and angles and things, they've just been flipped or translated and that kind of thing. So because these angles are congruent, we can say that this length here must be exactly the same as this, because they're the same corresponding sides of our congruent triangles. And this length here needs to be the same as this, because they are corresponding sides of our congruent triangles. So therefore, because the triangles are congruent, BE, let's just scroll down a bit more. BE is the same as DE, and AE is the same as CE. And then finally, the kicker to finish it, therefore, the diagonals bisect each other. Okay, the end. If you want to be really cool and smart about this, you put QED, which is Latin for quo est demonstratum, as far as I know, which means this is the thing that I set out to prove. Okay, if you put that at the end, no extra marks, just some kind of nerdy maths cool factor, I suppose. So I really encourage you to have a look over this one here again. It's complicated, it's long, but in it is a really rich task and will really stretch your mathematical understanding. Okay, so please, I'll probably try and get a chance to talk about some of these more complex proofs in class to make sure that we're also on the page and seeing things come out. But there's that one there. I don't want to go through the others because I want to give you a chance to have a shot at it by yourself first. Otherwise, come along to class with any questions that you might have, and I hope you enjoyed this video. Thank you.